now what I want to talk about, I'll leave those up for a second, is eigenvectors, eigenvalues, and eigenvectors. So for today and for most of the rest of the class, V is, if I don't say what it is, it's going to be a finite dimensional complex or real vector space. Okay. And we're especially now going to be thinking about these operators, which is another name for elements of endomorphisms of V, of L of V, of L of VV. Maps, linear maps for a vector space to itself. So remember, if I just have a function, I'm in the world of functions, there's not that much structure imposed. I can talk about things like injective and surjective. When we added the structure of a vector space, and we're concerned ourselves with structure preserving maps between vector spaces, linear transformations, we got more structure. And then when we concerned ourselves even more specifically with functions, endomorphisms or operators, vector functions from a vector space to itself, we got even more structure, right? So one of the theorems we proved, for example, was that to be injective, surjective, invertible, isomorphic all mean the same thing here, but certainly not anywhere else here. Right? Those are different concepts for functions, different concepts for linear transformations, although I can talk about things like the null space and use rank nullity to characterize injectivity and surjectivity, but here it was even more structure in terms of what was possible. And we're going to be using that structure to analyze these things. Okay, so now suppose that V is a, say, four-dimensional vector space, and it has a basis V1, V2, V3, V4. There's a direct sum decomposition that is associated to that basis, as I can certainly think about V as being the span of V1, direct sum the span of V2, span of V3, span of V4. Why is that? Well, to be a direct sum, I have to have two things, right? One is that every element of V can be written as the sum of elements of the subspaces. With W1 in whatever Wi and Ui, and the subspaces here is these spans. So every vector has to be representable that way, and second of all, every vector has to have a unique representation that way. Right? So what does it mean to have a unique representation in a subspace which is the span of a single vector? Well, we know that the span of a single vector is just the scalar multiples of that vector. Right? Span of Vi is the set alpha Vi with alpha in the field. And so that means that to have such a unique representation means that V can be written uniquely in the form alpha, alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4, and that representation is unique. But that's exactly what it means for V1 up to V4 to be a basis. Right? So to say that it's a basis and to say that this is a direct sum, it's the same thing. And so the idea of this section is that we're going to be looking for linear transformations. Given the linear transformation, we'll be looking for direct sum decompositions which are compatible with that linear transformation. As compatible as possible. And a lot of the rest of the class will be devoted to figuring out how compatible they can be and how good such a decomposition can become. So let's give a really simple example. Okay. So we're in this V1, V2, V3, V4 situation, and I can determine a linear transformation. So I'm going to write here a matrix. And here's some vectors. So we know that I can determine a linear transformation by telling you where it sends every basis element. So if I'm dealing with an endomorphism of V, a map from V to V, linear map from V to V, I'm going to say F gets applied to vector V1, and it's expressed as a linear combination of the vectors V1 up to V4. Those are the columns of this matrix. Well, what's the best possible situation we could imagine? It's that, well, it just sends each vector back to itself. That's the simplest possible linear transformation that's sort of maximally compatible with this basis. The matrix of that linear transformation, of course, would just be the identity matrix. The second most nicest linear transformation that I could imagine is, let's just let these be scalar multiplication. So then what would the matrix be? Yeah, it's just alphas along the diagonal and zeros everywhere else, right? So that's right. So this is a situation where it satisfies f of v1 is alpha 1 times v1. F of v2 is alpha 2 v2, and so on. And we'd like to look for situations like this and understand what these look like. So we could have a slightly less good example where, for example, f of v1 is a linear combination alpha 1 v1 plus alpha 2 v2, and f of v2 is beta 1 v1 plus beta 2 v2. F of v3 is v3, and f of v4 is v4. So that's almost as good. So what would that matrix look like? It's almost like the other one. The bottom part is the same, alpha 3, alpha 4. Zeros here. None of the v1s get sent to the v3s. None of the v3 or v4 get sent to v1 or v2. But this one is sort of arbitrary, right? Alpha 1, alpha 2, beta 1, beta 2. It's kind of a block diagonal. So in this case, F is compatible in the sense that it sends the span of v1 to the span of v1. It sends the span of v2 to the span of v2, span of v3 to v3, span of v4 to v4. Here it's almost as good, except that it sends a bigger span of v1 and v2 to span of v1 and v2. Yeah.
Where's the alpha from?
And in some contexts, this, when we're really lucky, we're going to be able to find a representation like this for f. In other words, we'll be able to find a basis that makes f diagonal. And when we're not as lucky, we might have something like this, for example, or even other worse things that sort of preserve this decomposition as well as we can, as much as we can. So we'd like a nice direct sum decomposition. Like that. Such that when I restrict f, so I just look at its image on U, I get, so in general, right, if I take f and I apply it to ui, I'm just going to get something which is somehow contained in V. It's not going to be anything special, but what we'd like is for f restricted to ui to map back to ui. Right? This direct sum is compatible in some sense with f if f just sends every subspace back to itself. That means if I write a matrix, if I write out a basis, if I write a basis of this and a basis of that, a basis of each of these, I'm going to get a matrix which is block diagonal. So let's make a definition. U is an F invariant subspace if for all u in U, f of u is also contained in U. So this is nice because we've sort of relaxed the requirement. We started out talking about bases, but now there's no basis in this statement, right? This is just a direct sum decomposition. And this turns out to be a really fruitful idea, right? So it turns out that if you want to analyze linear transformations without forcing them to be matrices, this idea of trying to break up the vector space into a direct sum decomposition of invariant subspaces is a really efficient way to characterize the linear operator. So let's consider some examples of invariant subspaces. So, an F can have some, like this F has this particular invariant linear subspace, but there are some subspaces which are invariant for all possible Fs. For all Fs which are linear transformations from V back to itself. So here's one example. Zero vector space. That meets the definition of an F invariant subspace. Because I take any vector in here, I always get the zero vector. I apply F to it, I get out the zero vector, which is in this space. Okay, so that's F invariant. Another equally trivial F invariant subspace is V. This is F invariant because I take any vector V inside this, I apply F to it. Well, the codomain of F is V, so I certainly get out something in V. And that's an F invariant too. Slightly less trivial examples, still pretty easy, but the null space of F. Right? Why is that F invariant?
It just gets mapped to 0, which is an F.
Exactly. Well, 0 is in this. Right? Yeah, so 0 is in this space. 0 is always in the null space. F maps everything in the null to 0. Therefore, this is F invariant. How about the range of F? Is that F invariant? It is. Why is that? Well, this is already everything F can hit. So if I take anything which is in this, I apply F to it, I'm going to get something which is in the range of F because everything that's in this already contains everything F can get to. Right? So I couldn't possibly get out of it by applying F. If U is in the range of F, F of U is in the range of F because U is in V. And the range of F is equal to F of everything. Okay. And so typically there'll be others. Not always, but usually there'll be many other F invariant subspaces. One example where these are the only ones is rotation, 2 dimensions. There's no invariant subspaces other than 0, null, and range, which are range is V and null is that. So these are the only invariant subspaces. Okay. Okay, so let's get back to this case of one-dimensional subspaces, one-dimensional invariant subspaces. So U is a one-dimensional F invariant subspace. Suppose that. What does F restricted to U look like? So I take a vector U, which is in the subspace little u. I apply F to it. What can I say about the result? Got a homework problem. What's a linear transformation from a one-dimensional subspace to itself? A one-dimensional vector space to itself. This is an example of that, right? Okay. It has to be scalar multiplication. Have a one-dimensional vector space, linear transformation. It must be scalar out multiplication. Okay, so let's make a definition. This is a very important definition. I'd say it's probably one of the most important definitions in the class. And one of those things that maybe one of the only things you remember from this class. So suppose F is a linear transformation from a vector space to itself. I have a non-zero vector in this vector space. And I have a field element such that F of u equals lambda u. Continue up here so everyone can see it. Because we have a one-dimensional space. We have a field, a vector, non-zero vector, a lambda, and F of u is equal to lambda u. Then u is called an eigenvector. This non-zero vector of F, and lambda is corresponding eigenvalue. Okay, so I want you to think about what's going on here. So I'm saying these come in pairs. Every eigenvalue has an associated eigenvector. Every eigenvector has an associated eigenvalue. But more than one eigenvector can share the same eigenvalue. Right. Nothing in this definition precludes that, but not the other way around. Right? F could not simultaneously be equal to lambda times u and alpha times u, where lambda is not equal to alpha. That doesn't make sense. But certainly there could be two vectors that solve this equation. For example, I could scale one of the vectors and it would still solve the equation. Okay. So they always go together, but more than one eigenvector can have the same eigenvalue. So let's see some examples. Okay. So let's start out with, here's my linear transformation. Here's my eigenvalue. And here's my eigenvector. Or eigenvectors. So first let's consider the identity transformation on a vector space. You think of an eigenvalue or eigenvector that goes with that. 1. Right? This is by definition for all v, I'd v equals 1 times v. Right? So So 1 is an eigenvalue. Eigenvector is any v, which is not 0, because our definition required it be non-zero. So any non-zero v is an eigenvector. How about f equals alpha times the identity? What do I get? Yeah, so the eigenvalue is alpha, and the eigenvector is the same. Any non-zero v is an eigenvector that goes with that eigenvalue alpha. Okay, so here's a more abstract version. So remember this linear transformation, which is I draw a line in the plane, and I think about the vector space of arrows that start at that point on the blackboard, and the linear transformation is I reflect across this line. Okay. Let me pick two vectors that are easy first. Let's call this v1 and v2. Is v2 an eigenvector? So what's f of v2? v2. So that's an eigenvector, just like this one, with eigenvalue 1. So 1, v2. What about v1? So v1 gets sent to negative v1. That means its eigenvalue is negative 1. My 1s are sort of heterogeneous here. Okay. And remember this, we saw that when we picked that particular basis, v1, v2, v1, v2, the matrix for f is -1, 0, 0, 1. Okay, so this is a theme we'll keep seeing. If you make your basis out of eigenvectors, your matrix is really nice. If you pick another vector, which is not an eigenvector, this is not an eigenvector, right? Because its image under f is not a scalar multiple. If you build your basis from non-eigenvectors, you will not get a nice matrix. Right? Well, you might get lucky in some sense. Something nice about your matrix, but it's not going to look like this. Right? It's not going to be diagonal. And we'll prove this stuff properly. Give you an idea where we're going. Okay, how about I take any linear transformation f, how about the eigenvalue 0? What could be an eigenvector associated to the eigenvalue 0? So that means it's going to have to solve the equation f of u equals 0 times u. Sorry?
Any u?
No, not any u.
It's not equal to 0.
Well, if f is the identity transformation, then that would be 0, u equals 0 u. So I'm saying for an arbitrary f. So we have a name for this. This is the null space of f. Okay. The null space of f, set of all vectors, which when I apply f, I get 0. So things that solve this equation this is another way of saying the null space. So the null space is the eigenspace, that is a set of all eigenvectors associated. So the null of f is the eigenspace of 0. Where eigenspace means set of all eigenvectors associated to the eigenvalue 0. Other eigenvalues can have an eigenspace too, right? So that one is kind of special. So our space, L of V, L of VV, and V. We were arguing earlier that it was a ring. You're allowed to multiply, but even more fundamentally, it's a vector space, so we can add and subtract. Right? So our eigenvalue equation, which we just erased, f of u equals lambda u. That's sort of this eigenvalue equation. Eigenvector and an eigenvalue together solve that equation. I can also think about that as lambda times the identity applied to u. Right? But now this thing is itself a linear transformation. I have a linear transformation over here in LV. I have a linear transformation. So f is in LV. This is in LV. And then L of V is a vector space, so I'm allowed to add and subtract those. So I can define f minus lambda I v. And when I apply that to u, up here I would get 0. This is just rearranging this equation. Subtract this side from that side, pull the u out using distributivity. So this gives me another eigenvalue equation, right? Another way to characterize what it means to be an eigenvalue. That is, it's a u such that f minus lambda identity of v times identity of v is equal to 0. So we have multiple ways of characterizing what it means to be an eigenvalue. Lambda is an eigenvalue. So now I'm not even saying what the eigenvector is. Because of this, I can sort of abstract it away a little bit. Lambda is an eigenvalue of f if and only if f minus lambda I v, this thing, has some non-zero vector u, which when I apply this linear transformation, I get 0. That means it has a null space. Non-zero null space. Another way of saying that is not injective. Now we had an if and only if. Now because of this theorem that injectivity, surjectivity, and isomorphism collapse, in the case of endomorphisms, we have, this is also the same as is not surjective. Well, that looks different, right? If and only if this is not invertible. So if you've seen this before, maybe you had a determinant to figure out whether something was invertible, and then you use this characterization to define an eigenvalue. Another way of saying that is if and only if f minus lambda I v is not an isomorphism of vector spaces with v to itself. Okay, so what that tells us is that we have, if we're interested in just the property of whether lambda is an eigenvalue, we have lots of different choices that we could use to prove something as an eigenvalue. And what's great about these is that they don't actually require that I find the eigenvector. Right? I can prove something like that f minus lambda is not identity, is not surjective without figuring out what the eigenvector is. So I might be able to show it has a certain eigenvalue without actually giving the eigenvector. And for very large problems, sometimes that's the real situation. You can prove that there's an eigenvector, we say eigenvalue 1, but finding the eigenvector is like impossible because the thing is enormous. And that's actually quite common.